So in this video, I'm going to recap Taylor series and how it can be applied for linearizing functions. So the first thing to note is that Taylor series is all about rewriting a function. It can be any function, and it's going to be as a polynomial. So for example, I could write the function f of x is equal to e to the x as a polynomial. Even something like sine of x could be written as a polynomial. And really kind of disgusting and gross functions. So let's pretend I had like something like this, x plus 3 squared all to the power of x. So something like this is going to be quite difficult to work with in that form. Imagine if you wanted to take a derivative or an integral of that function, it would be pretty difficult. Whereas if we rewrite this as a polynomial using Taylor series, polynomials are really nice to work with. You can take derivatives easily, you can take integrals easily, and it's a continuous function as well, which makes it quite nice. So that would be an example of where a Taylor series might be used. So the other point to note about Taylor series is that it's applied about a point of interest. So you need to pick an x value, in this case we're calling it x equals a, that you'll want your Taylor series to be accurate about. So this here is the actual equation for Taylor series. So what we're doing is defining a new function, f of x, and it's going to be equal to f of a, so it's the function evaluated at your point of interest, so it could be any of these, alright, just substituting in your a value to them. And then what you see here is we have a summation sign. So we're going to pick up a number of different terms. We start at n equals 1, and we take all the integer values above that. So we take then n equals 2, 3, 4, 5, and so on, and you can see that this goes up until we reach infinity. So we'll talk about that in a second. Inside this summation, what we have is f. This isn't a power of n. This is telling you how many derivatives to take of our function. So if n is equal to 1, we would take one derivative. So we'd get f dash. And we then evaluate that derivative again at our point of interest. So substitute in x equals a. On the bottom line here, we have n with a little exclamation mark. This is n factorial. We've then got x minus a, and this is a power this time, to the power of n. So we go through and figure out all these derivatives, all these substitutions of x equals a and so on, and we end up with having basically an infinite number of terms that we pick up. Alright, so as long as we apply this with our infinite number of terms, what we're going to find is that we end up with an exact representation of our function. So instead of using it as e to the x, we could use it as our Taylor series polynomial. Now, obviously it's impractical to pick up an infinite number of terms. Okay, so what we end up doing in reality is cutting off this Taylor series after a certain number, and that is called the truncated Taylor series that you see here. So what I've done is I've flipped over our equal sign to be a approximation. It's approximately equal to. And that's because now we've got f of a, which is the same as before, but the summation sign has changed. So now we're starting at n equals 1, but we're cutting it off after capital N terms. So if n was equal to 3, then we would have 3 terms that we'd add out of our summation symbol there. So let's write out the first couple of terms at least of this truncated Taylor series. So we're going to have f of a. So we start with n is equal to 1. So if we substitute that in, we're going to get f dash of a. It's going to be 1 factorial and x minus a to the power of 1. Alright, so now we'll go to the next integer, which is n is equal to 2. So we'd end up with our second derivative evaluated at a. We'd end up with 2 factorial and x minus a to the power of 2. So that's where like the second order polynomial comes in, because if you expand this out, you're going to end up with an x squared. Let's do one more. So the next integer would be 3. So it's going to be the third derivative that we need to take of the function, evaluated at a, and 3 factorial x minus a to the power of 3. Alright. And of course you can keep going for as many terms as you want or need. There are equations which will quantify the error for you in your truncated Taylor series, depending on how many terms you include, but I'm not going to go into any detail on that in this video. Alright, so I've stolen this animation off Wikipedia, and what it's showing us is the exponential function, so e to the x, which is this blue line, and that's the exact value of the function. And what we've got in the red is the truncated Taylor series, calculated about our point of interest x equals 0. And what we can see is that this n value is changing, and that's changing how many terms that we're picking up in the Taylor series. So we can see that when the n number is low, we have the least accurate approximations of our function about this point of interest. And as that n value gets higher and higher, it gets much more accurate to the function. What you can also note is that the shapes of these functions match what you'd expect. So for example, when we get back to n is equal to 0, what we see is it's a straight line. When it's n is equal to 1, it ends up being sloped, which would be equivalent to y equals mx plus c for an approximation. When we have n is equal to 2, it looks like a quadratic function fitted through it. N is 3 is a cubic, and so on. Alright, that's because basically the number of terms that you pick up corresponds to the order of the polynomial that you're fitting to your function. We're going to talk about linearization, and this corresponds to the specific case when n is equal to 1. Alright, so when n is equal to 1, which we'll see now, you see it's like a straight line fitted through, which, as I said before, could be equivalent to y equals mx plus c. So whenever people talk about linearizing a function, essentially it's just a case of applying your Taylor series and cutting it off at n equals 1, which we'll see in a moment. Alright, so jumping back over to this page, what I'm going to now do is write out the linearized version of a function using Taylor series. So what I just said a moment ago was that basically we want to pick up the f of a and just one of the terms that falls out of our summation sign. Alright, that's because this is the linear part. You're going to see in a moment that we can rearrange just this bit of the equation to end up looking like y equals mx plus c. Alright, so scrapping all of this, we can write our function as f of x, and I should probably put in the approximation thing because it's not going to be very exact. And I'll simplify this a bit, so this becomes f dash of a, it's divided by 1 factorial, which is 1, and then we've got x minus a, and it's to the power of 1, which I'll just drop as well. So this is what you need to apply if you're looking for a linearized version of your function. So I'm just going to show you that this does match y equals mx plus c. So if I rewrite this with slightly different notation, so f of x, this is kind of equivalent to the y in that equation. F of a, I'm just going to leave for a moment. And then this I'm going to expand out the bracket. So we get f dash of a multiplied by x. It's actually going to be a negative from in here. So it's minus f dash of a multiplied by a. So if I pop this together, I'll leave this out the front, so f dash of a times x. Putting these together, because these are going to end up both being constants. So f of a minus f dash of a times a. So what this is f dash of a, this is equivalent to like the m in the y equals mx plus c equation, because this is just going to be a number that falls out when you evaluate what the derivative is at our point of interest. So this is m times x, and then this stuff on the end, again, it should just be a constant. So this is going to be equivalent to the c in y equals mx plus c. F of a, again, is just evaluating it at a, f dash of a, evaluating it at a, and multiplying by that a value. So you can see, hopefully, that it ends up making your, whatever your function is, a linear function, and remember that it's going to be accurate about your point of interest. Alright, and as you drift further and further away from that point of interest, it becomes less and less good at predicting the function. I'm going to leave it there for this video, and I'll do another example one later on.